We are dealing with the knowledge area mechanics, and we're going to look at the graphical interpretation of displacement and velocity. Let's see what we mean by average velocity. The average velocity of an object during a time interval is equal to the slope of a straight line joining the initial and final points on a graph of position versus time. Here we need the average velocity between points A and C. Between points A and C. If we need the average velocity between A and C here, there's A and that C. What do? We have a line joining A and C. And then we determine the slope of that line. So here, how do we determine the slope of a line? In mathematics, slope is defined as change in y over change in x. So we say y2 minus y1 is equal to x2 minus x1. That is the definition of a slope in mathematics. That means we have to take the vertical change, means the change in y over the horizontal change and the change in x. But since here we're dealing with velocity on our y-axis, it is x2 minus x1 all upon, and on our x-axis we got time, so it's t2 minus t1. So essentially this and that is equal to that. So on our y-axis we've got position, and x2 minus x1 denotes the position that's changing. Now if we look at this and we say what is the velocity between A and C, so we look at A and we say okay, A is there, and there we got, so our change in x is 8 minus 2, which is 6, and our change in time is from here to there, which is 6 minus 2, and that's 4. So which would mean that we have change in x is 6 meters, all upon the change in time is 4 seconds, and that gives us 1.5 meters per second. That's the average velocity, and it is plus. So which indicates that if that's a direction as plus, that means the average velocity is in that direction. Alright, so here we took the slope and we said slope like that. We have that line, and we said change in x upon change in t, and the slope is positive. Now let's look at the average velocity between C and E. That means we want the average velocity between C and E. What do? We connect a line CE, and we then determine its slope. So we determine the slope, the change there, and the change here. Here we know we got 8 and there we got 4, so the change is 4. Since it's 8 minus 4 is 4. And here we got 10 seconds and that's 6 seconds, which would mean that it would be 10 minus 6, which is 4. So that's 4, and this is the change here is 4, but here we need to be careful because in terms of our definition now, we have that as our initial distance, and that's our initial and that's our final. So we say x2 minus x1, which would mean is equal to x2 minus x1, or final minus initial, and then t2 minus t1, and that would be equal to 4 minus 8 meters all upon 10 minus 6 seconds, and that gives us minus 4 meters all upon 4 seconds, and that gives us minus 1 meter per second. That means that is a negative velocity of 1 meter per second. So our average velocity is 1 meter per second, but it's moving in that direction. Now, in here we have determined the average velocity between A and C and between C and E. But generally, sometimes we don't want the average velocity. We want to know what is the exact velocity at a particular point. So let's say, for instance, we want to know the velocity at point A, or at point B, or at point C, right? Any point on the curve, rather than the average. So then we need to determine the velocity at a particular instant. And when we want to determine the velocity at a particular instant, then we need to look at another concept which we call instantaneous velocity. So, for instance, many motions do not occur at constant velocity. Right? So we don't have a position time graph that is normally a straight line. Right? So position time graphs are normally not straight lines, like I've shown you above. There you've got a position time graph that's not a straight line. So a more realistic situation is it's one in which the velocity continually changes. So if I go backtrack here, that means we want to know what is the velocity at that point, and at that point, and that point, and that point, and that point. These velocities are different as this particular particle or object moves. And we are interested in what is the velocity at each instant. So if we want to determine the velocity of an object at any particular time on a position time graph, we will need to determine the instantaneous velocity. And what is the instantaneous velocity? The instantaneous velocity is a velocity at any moment, or I could say instant or moment. and it is defined as the average velocity during an infinitesimal means very, very, very short time interval, right? Very, very short time interval. So we virtually want the instantaneous velocity at a particular instant in time. Now let's look at this. How do we go about determining the tangent at a particular point on a curve? And here I have a position time curve. There's position against time. Now this particular curve that we have here is actually modeled by the equation x is equal to at squared. X is the position, so that's position, and that's time, and A is a constant. And let's say this constant, it's a physical constant, and let's assume its value is 1. So let's say A is equal to 1. I am not reflecting its units, but we know that whatever its units are multiplied by the units of time, it should give you the unit of position, which is meter. So at this point in time, let's assume A is equal to 1. So if we have this equation modeling it, now we want to know the tangent of a line at point P. And that means we want to know if a tangent is drawn to point P, we want to determine its slope, because the slope of that tangent is going to give us the instantaneous velocity. So let's look at this further. So if I have now x is equal to at squared, and let's say a, we said it's 1, so I have 1 times t, so let's say we're at 3 seconds, so it's 3 all squared, which means that is equal to 9 meters. So x is equal to 9 meters. When the time is 3 seconds, x is equal to 9 meters. And let's take another point. Say x, when we want to determine it at 4 seconds. So let's say this is a 4-second mark. And that would be 1 times 4 all squared, which gives us 16 meters. So we say, okay, here at this point, we have x is going to be 16 meters. So we say, okay, if we want change in x, that is 16 meters, this is 9 meters. What's our change in x? It would be 16 minus 9, and that would give us 7 meters. So we got change in x as 7 meters. What's our change in time? It's 4 minus 3, so our change in time is 1 second. So if we want the gradient now for this particular chord PQ, we find that it is equal to, we want the velocity there, we find, okay, so let's say gradient is equal to 7 meters, because that's what we have there, and upon 1 second, and we find that the velocity of the average velocity is equal to 7 meters per second, right? And it's positive. Right, but what we want now to do is we have okay, so what we have now is we want to move closer towards P. So let's say, for instance, we've got Q here, and if we move closer towards P, now we've got Q, and we need to determine that velocity. And so what do? The same thing. That's my change in x. So that's my change in x, and this would be my change in t. But let's say I'm moving closer. Remember, I started at 4 seconds. Let's say I move closer and I come to 3.1 seconds from there. And we need to know what would that give us so that we can work out change in x. Now, if we want to work that out, we say, okay, we have the gradient again, and the gradient will be equal to, we know change in x upon change in time. But let's first determine what x is at, so x at x, we know x is equal to x is equal to a t squared, and that is equal to 1 times, it's going to be 3.1 all squared, and that is going to be equal to 9.61 meters. So that means here it's going to be 9.61 meters. And what would our change in time be? So that's x. So we want our change in x. Our change in x is going to be 9.61 meters minus 9 meters. I have it here. And that is equal to 0.61 meters. What is our change in time? Our change in time is equal to that minus that, which is 3.1 second minus 3 seconds, and that gives us 0.1 second. So we got our change in x and we got our change in t. Now we want to find the gradient. So what's the gradient of this? It's going to be 0.61 meters all upon 0.1 second. And what is the gradient here now? It's 6.1 meters per second. Right, we started off by having 7. So as you can see, as this is getting closer and closer till we get to point P where we have a tangent. And then we need to determine the slope of that tangent. Now, what I've done here is I've just illustrated how the gradient of that chord is slowly changing as it's approaching the slope of the tangent. Now here it is illustrated nicely in terms of values. Okay, so let's look at that. So we said this is our equation which we use, and when we had 4 seconds, remember that was 16 and the change was 7 meters in position, and that's 1 second, so the gradient or the average velocity was 7 meters per second. Then I took 3.1 and we find that at 3.1 x was equal to 9.61 and the change is 0.61 meters, and the time was 1 second, and see what the velocity was. Okay, the velocity is 6.1 meters per second. Then if we get still closer to 3, because remember we took our time, we need to determine our instantaneous velocity at at 3 seconds. And then if we take it even closer, notice what happens. You got 6, it comes to 6.01, it comes to 6.001. If I took this even closer to 3, this would then go to 6.0001 meters per second. The important point of this is you can see that the limiting value of the gradient chord is 6 meters per second. That's the important point. And that limiting value is approached when change in t is very, very small. When change in t is very, very small. There. Right? So you need to know that when the time interval is very, very short. Right? So when the time interval is short. Okay, so that is your limiting value. And what we sometimes do is we say, this is how we write that. We say V average is equal to, say, change in x upon change in time. Then we say the limit is as change in t approaches 0. Then the limit of the velocity is equal to 6 meters per second. So if we take that average and the limit of that average velocity as it approaches change in time when it's 0, like as you can see here, the difference is that, and if you let the change in time approach 0, your limiting value would be 6 meters per second when the time is very, very short. Alright, so this is how we write it mathematically. You will do this limits in grade 11 if you're doing mathematics, but the important point to remember here is that when the line is a tangent to the point on a position time graph, then that gives you the instantaneous velocity. So whilst I've shown you the mathematics here, you need to understand the conceptual implication of instantaneous velocity. So here figure shows as Q approaches P, the chord becomes a tangent. Right, so what we're saying, so here's a chord, and as this moves that way, as this is moving that way towards P, where you got that, and as it gets closer towards P, the chord actually becomes this tangent line. And that's important. Hence, we got that the limiting value of 6 meters per second is the gradient of the tangent P. And then since the gradient of the tangent represents the gradient of the curve, since it represents the gradient of the curve, then the 6 meters per second is actually the gradient of the curve at point P, which means we are getting the instantaneous velocity at point P. But now let's look at various tangents on a line. So here we have, say at this point we want to know the tangent. At that point we want to we draw a tangent. There we draw a tangent. And these are all tangents. And the tangent touches one point on the curve. And if it's a straight line, then the tangent line and the straight line are the same. For instance, like here, it would be if it's a straight line, then the tangent is in line with the curve. Now here, for instance, if we do that and we do this, so we got, here we have that. Here we have this change in x. In our situation, change in x upon change in t, which means that gives us a positive slope. Here the slope is 0 at B. Here we need to have that slope, and this is a negative slope. So you need to be able to see from a graph whether the slope is positive or negative. Here it's 0. There is positive. The slant is the same as that. Right, so you need to determine the slope. And from the slope or the steepness, you should be able to determine whether the velocity is increasing or decreasing. That's important because we're going to still be dealing with that. Okay, now we're looking at varying velocity. So the displacement during respective time intervals is given, and the velocity we need to calculate it. Whilst we need to calculate the velocity, I have already calculated the velocity, but I'll give you an indication of how we get it. Now we know velocity, so we given A, the time interval A, and the displacement is 3 kilometers, and that's the time interval. We want to calculate the velocity, and that is equal to change in x. So change in x is actually displacement, which gives us 3 kilometers, and the time interval is 0,1 hour, which is then equal to 30 kilometers an hour, which is that. Let's look at the next one. V is equal to change in x upon change in t, and that would be, we got 15 kilometers, all upon 0.3 hours, and that gives us 50 kilometers an hour. Right, and then that's at B, and that would be at A. C, as you can see, is equal to 20 kilometers an hour. Now we've got this, we need to have a graph that's plotted. So here we have now determining the displacement from a velocity time graph. So a car moving with different velocities during different time intervals. Here we have it. Now, the car was moving at 30 meters per 30 kilometers an hour, and then we see that the velocity suddenly becomes 50 kilometers an hour. Now we know that that the car cannot change its velocity that quickly, but I mean, cars these days can accelerate within a short interval, but for simplification I have just drawn it as a straight line. Right, so it makes our calculations easier. So here we have this, and we want now the area underneath the graph. So let's say that is A. We want this area, and then we want this area, so we want that area, and then we want that area, and then we want this area. So if we have the area below a velocity time curve, we find that we can now determine the displacement. So if we say change in xa, which would mean v change in t, and that is equal to, we take the first one, which is 30 kilometers an hour, and the time there is 0.1 hours, and that gives us 3 kilometers. Then we want change in x, the area under B, and that is equal to v change in t, and the velocity there, as you can see, is 50 at 50, which means it's 50 kilometers an hour, and the time interval is from 0.4 there to 0.1 there, and that is gives us 0.3 hours, which then is equal to 15 kilometers. Then change in x of c would be a 20, so v change in t is equal to 20 kilometers an hour, and the duration here is equal to 0.1 hours, and that gives us 2 kilometers. So there you have that, and if we look at our total, which is 3 and 5, 15 is 18, and our total displacement is equal to 20 kilometers, which we see here. It's 3, 18 plus 2 is 20. So here we were given a velocity time graph, and we could determine the displacement. Okay, so there you have that. Now let's look at how we determine the displacement from this graph. Here you have, for instance, okay, this is given in terms of meters per second and time in seconds. So if we want to, we say, okay, we want this area, let's call it A, and let's call this area B, and let's call that area C. So we want to determine the displacement. So if we want to determine the displacement of area A, which means x, or change in x of A, is equal to, it goes to 2 meters per second, 2 meters per second, and what's the time? The time is 2 seconds. So that would mean our displacement there is 4 meters in a positive direction. Remember, it's a rectangle, so to get the area, it's base times height or length times breadth. And here change in x of B is another rectangle, so we would say that is equal to 3 meters per second, because that's 3, and the time interval here is equal to 2 seconds, and that gives us plus 6 meters. Then change in x of C. Now here we have that graph, and we need to determine that displacement, and that would be minus 3 meters per second as reflected there. And the time interval is from 10 to 4. The change is 6, so it's 6 seconds, and that is equal to minus 18 meters. So there you have plus 10, and here minus 18. So what's your total displacement? Total displacement is equal to minus 8 meters, and that means the displacement is towards the left. It's only giving you an indication of the direction of the displacement from the point where it started. It doesn't give you the position, and that is important. In order to know exactly where this object or particle is, we need to be given the initial positions. Alright, so there you have that. Now let's look at one more where we determine the area. So now here we've got the area in which we have a changing velocity during part of its trip. So if we want to determine the area, I would say we'll look at this area, and then we'll look at this area here. So if, for instance, we want we could do that area, work out this area. And the reason is I could have broken this up into a rectangle and a triangle like this, but I prefer doing this because the shaded area is actually a trapezium. And then here we can work out that area. And that's easy because that's a rectangle. So if we now look at the area, so what is the area of the total area? So we say change in x total would be change in x of A is a trapezium plus change in x of B, which is our rectangle. Now if we look at the trapezium, how do we get the area? We say that's 20 and that's 40, so we know it is half the sum of the parallel sides, which is 20 plus 40 upon 2. And what's the change in time? The change in time is 0.2, which then we know this is in seconds, and we know that this is in meters. So maybe let's just write it properly. Let's do that and say that gives us meters times we have 0. Okay, 0. So that's not meters. We need to be careful because I'm saying it's meters. It's not meters. It is kilometers. See, it's velocity, so it's kilometers an hour. Kilometers an hour. Right, kilometers. Let's just do this properly. Okay, so let's say it's equal to 20 plus 40 upon 2 kilometers an hour times our total time is 0.02 hours, and that gives us 0.6 kilometers. So this one here is for changing x of A. Let's look at changing x of B. That would be fairly easy because it's a rectangle, so we know from there to there is 0.02 hours. Okay, and the height is 40, so we have 40 kilometers an hour times 0.02 hours, and that gives us 0.8 kilometers, which means now total change in x t change, which means change in xt is equal to, we add the 2, and that's 1.4 kilometers, and it's plus, so it means the displacement is in that direction, moving towards the positive direction. Okay, now let's look at the exercise. We say, what physical quantity can be obtained from the slope of a position time graph? Okay, we've been dealing with that. What physical, from a position time graph, we can obtain the velocity. Okay, we can obtain the velocity. And what physical quantity can be obtained from the area of a velocity time graph? We know that that would be displacement. Right, so from the slope of a position time graph, slope gives us velocity, and area of velocity time graph gives us displacement. Now here, the next one, we say, can an object with a varying speed have a varying speed if its velocity is constant? If yes, give examples. Right, now what's being asked, if I have a velocity time graph, velocity there, time there, and the velocity is constant. If the velocity is constant, can its speed be varying? Alright, that's the question. And as you can see, the velocity is constant there, and speed is essentially the magnitude of the velocity. So here in this case, we say no. Since, the velocity is constant, so if velocity is constant, so when velocity is constant, its speed is constant. Its speed is constant. And here in this case, the direction of the velocity is also constant. Right? So when velocity is constant, its speed is constant. Let's go on to the next one. Now here we have a train that moves along a straight portion of the road of a track according to the graph of position versus time. Now we want to know the average velocity of the total trip. Here it's moving from A, it moves from 0 to A, then to B, and then it's at C. Right? We want to know the average velocity for the total trip. So let's work that out. We've been dealing with that, and how do we do that? In order, we have our position time in centimeters, and our position is in centimeters, and our time is in seconds. So if we want to know the average velocity, we need to have a straight line joining that point and that point, which is given by this line. That will give us an indication of the average velocity. So let's say for the total trip, we want the average velocity, so V average is equal to change in x upon change in time. And what is the change in x? That would be the change in x, and that is equal to from 10 to 0. That would give us change in x is equal to 10, and change in time is equal to 12, because we're determining the slope of that line, which is equal to 10 centimeters all upon 12 seconds, which then gives us plus 0,8 centimeters per second. So that's the velocity. Now we want to know the average velocity during the first 4 seconds. So if we want to know the average velocity during the first 4 seconds, we say, okay, right, first 4 seconds, that means we want to know the average velocity there for the first 4 seconds, and that would be change in x upon change in time. And as you can see, that's a straight line graph. So what would that be? So this is A and this is B. So for that 4 seconds, the average velocity would be v is equal to change in x upon change in time. What does that tell us? It's 4 centimeters. So it's 4 centimeters upon 4 seconds, which says it's plus 1 centimeter per second. Right? But anyway, any slope we take, we'll find that velocity is constant along along the origin and A. Alright, so we have that there, and let's see the next one. It says the average velocity during the next 4 seconds. So the next 4 seconds. So what's the next 4 seconds? We're looking at that. Alright, so the next 4 seconds, we say C. What is the average velocity there? We would say V is equal to change in x upon change in t, and I just showed you earlier that the slope for this would be equal to x2 minus x1 upon t2 minus t1, which would mean 0 upon whatever time interval you have, which is in our situation would have been 4 seconds, and 4, I'm always making this error here, is 0 centimeters and 4 seconds, so this would be 0. And which means the slope is 0 at that point. Slope is equal to 0, gradient, so there's no velocity, and what has happened, as you can see, from there to there, after 4 seconds, it's still at the same position. That means it has stopped. Right, we won't know what's being done while it stopped, but we know that it has stopped for that 4 seconds. Then we've got D, and D says what is the instantaneous velocity at t equal to 2 seconds. Right, so we have dealt with instantaneous velocity, and we say, okay, let's see what's the instantaneous velocity. So instantaneous velocity. But where we're looking at 2 seconds, okay? That means we want to know what is the instantaneous velocity at this point. If we want to know the instantaneous velocity at this point here, what do we need to know? We have to have a tangent drawn to that line. But this is a straight line. It's not a curve. Then we have to go through that procedure to determine what is the tangent, the slope of the tangent. Here, your line and your tangent is the same. So that means the velocity that we got earlier here, the instantaneous velocity is equal to 1 centimeter per second. All right. Since we have a straight line and the slope of a straight line, okay, line is constant of a position time graph. Right, now let's look at, we say here, what object moves, when an object moves with constant velocity, does its average velocity during any time interval differ from its instantaneous velocity at any instant? So here we have that. So here question is being asked, if something is moving at constant velocity, does its average velocity during any time interval differ? Doesn't, because if we have a constant velocity and I take that, my average will still be the same. If I take another time interval, average will still be equal to the constant. And it's like saying, if I have 2 plus 2 plus 2 plus 2, what's my average? It's still 2. Right, so that's important. And therefore, the instantaneous velocity at any instant is also equal. So we can say, does the average velocity differ? No. Right? When moving with constant velocity, when moving with constant velocity, then we have this relationship. Then velocity, if it's constant, then it's equal to the average velocity, and we would say that it is during that time interval also equal to the instantaneous velocity at any instantaneous velocity. Right, at any instant. Right, let's look at the next one. There it says draw a position time graph for a motion of a particle whose position is shown. Let's assume that the time interval as it changes its location is 1 second. Okay, so here you got A going to B, going to C, and from there it goes to D. And remember, this is all along the line. And we're saying, let's say it takes 1 second for every as it changes its location. Now let's draw a position time graph. So here we have now, we have A is at +1 and B at +2. So after one, there we have A. Then we go to B. B is at +2. And then C after the 3rd second is there. And then D, it comes back to the origin. And then E here at -1. So E we have here, and let's just draw it maybe. We got E, and then we got -2, which is here, and that is F. So if we draw the line like that, we have that, and moving there. Right, that's your position time graph. So that's your position time graph. Let's go to the next one. It says here, you're given 3 graphs versus time for objects moving from the axis. Which of these graphs is not physically possible? So if we look at this here, for you have the position changing with respect to time. Here clearly you can see the position there and the position there. It's like having 2 positions at the same time, and that in Newtonian mechanics, or when we deal with classical theory, we can't have the object at 2 places at the same time. So that's not possible, and this here is possible. Let's look at the next one. Here we say, what is the average velocity? We want to know the average velocity when this starts from rest and goes 40. So it's 40. So it goes there. Alright, so we have moving at 40, right? It's going up to 40, and then it maintains that velocity till there. Then it comes back to 20, and then it carries on there, and in 0.6 hours it's back. The velocity is 0. Now we want to know what is the total displacement for this, and in order to do that, we say, okay, what we can do is we say we have that area, and then we have that area, and we can take that area. So we could say this is A, this area is B, that area is C, and that area here is, say, D. So we could have that area there, like that, and we can have this area there, and then we can have that area, and then we can have that area. So we need to determine each area underneath the curve. So let's say we start with that, and we say change in x a is equal to, we can, because it's a triangle, we know it's half base times height, which we can say is equal to a half times the base is 0.1 hours, and the height is, as you can see, 40. So we say times 40 kilometers an hour, and that gives us 2 kilometers. So let's maybe just say 2 kilometers there. Then we look at the next one, and we say change in x of b, that would be base times height, and that would be 0.1 hours times 40 kilometers an hour, and that would give us equal to 4 kilometers. Then we go to the next one, and here we want that now, and here we say change in x of c is again equal to a half base times height, and that would be a half and times 1 hours times what is the difference? That's 40 and that's 20, so the difference would be 20 kilometers. If we want the area, kilometers an hour, okay, which means we have 40 minus 20 kilometers an hour, and that would be equal to 1 kilometer. 1 kilometer. Right, and all these are pluses, also plus. And then we go to the last one, and that one we say we want to know this area, which should be fairly easy. Change in x of d is equal to base times height, which is 0.4 hours, because that would be that 0.6 to minus 0.2, and times the velocity is equal to 20 kilometers an hour, and that gives us 8 kilometers. So then what is our total displacement? Total displacement is equal to, if you see, we have 2 plus 4 is 6, plus 1 is 7, plus that, so it gives us 15 kilometers. That's our total displacement. But we want now the average velocity. So if we want the average velocity, so we can say average velocity, V average, is equal to change in x upon change in time. Change in x is equal to 15 kilometers. And what's our change in time? Our total change in time for that trip is 0.6 hours. So it's 0.6 hours, 0.6 hours. And what do we get? We get 25 kilometers an hour. That's positive. So that is the average velocity. If we look at this curve here, and I have to draw that, see, that's 40, that's 20, so that's 30 there, so 25 is somewhere here, and that would imply that that is the average velocity. Average velocity. And if we got the average velocity there, if we got the average velocity, let's just neaten this up a bit. Here we got the average velocity, right? So whilst you got this object moving, increasing its velocity to 40 and then slowing down, the average is equal to 25 kilometers an hour. And if you work out the displacement underneath that curve, you'll get 25. You will get 15 kilometers. Right. So there we have it. And see you the next time.